Hello students, welcome to the lecture on Premutations and Combinations. And after this lecture, we will be able to learn the following objectives. Explain the meaning of permutations, discuss the combinations, define the binomial theorem. Let's start with the concept of permutations and combinations. Suppose that we have n distinct objects a1, a2, a3, so on till an. The objects might be different fruits such as an apple, a pear, an orange, a banana, and so on. In how many distinct ways can we rearrange our n distinct objects, say our fruits, in a line? One arrangement is orange, banana, pear, and apple. An alternative way of saying this is, in how many distinct ways can we permute the order of our n distinct objects? Suppose that we have only 4 fruits, an apple, a pear, an orange, and a banana. We also have 4 positions to fill. We have 4 choices for the first position. We might pick a banana, for example, but for each choice for the first position, we will have 3 choices for the second position. If our first choice was the banana, then for our second choice, we have only the pear, orange, and an apple left. After that choice, we have only 2 choices left for the next and third slot. And for the last slot, we have only 1 choice, in fact, no choice at all. We can generalize our discovery. If we have n distinct objects, then we have n ways of picking the first in line, n minus 1 ways of picking the second in line, n minus 2 ways of picking the third in line, 1 way of picking the last object. With each of the n ways of picking the first object, we have n minus 1 ways of picking the second object, and with each of the n minus 1 ways of picking the second object, we have n minus 2 ways of picking the second object, and so on. Each possible choice for rearranging the distinct elements is called a permutation. We conclude that the total number of distinct objects is n into n minus 1, n minus 2, n minus 3, and so on. 1 permutations of n, the terms are multiplied because for each choice at every position, you have any one of the remaining choices. This special product is called n factorial and is written as shown. N exclamation equals to n into n minus 1 into n minus 2 into n minus 3, and so on till 1. It is the simple product of all the numbers from 1 to n. For n distinct elements, we have a total of n exclamation. Permutations. In how many ways can we permute our 4 fruits? Because n takes the value 4, the answer is 4 exclamation, which equals 24. Let us take the example of the 4 letters A, B, C, and D. In how many ways can we choose 2 letters out of the 4? Let us look at the screen for better understanding. By dividing out the common products 1 into 2 in both the numerator and the denominator. To see this result clearly, let us write out the permutations AB, CD, AC, AD, BC, BD, BA, DC, CA, DA, CB, DB. Let us now discuss permutations. Consider the following problem. In how many ways can 8 horses finish in a race, assuming there are no ties? We can look at this problem as a decision consisting of 8 steps. The first step is the possibility of a horse to finish first in the race. The second step, the horse finishes second. The 8th step, the horse finishes 8th in the race. Thus, by the fundamental principle of counting, there are 8, 7, 6, 5, 4, 3, 2, 1, which is equal to 40,320 ways. This problem exhibits an example of an ordered managed arrangement, that is, the order the objects are arranged is important. Such ordered arrangement is called a permutation. Products such as 8, 7, 6, 5, 4, 3, 2, 1 can be written in a shorthand notation called factorial. That is, 8, 7, 6, 5, 4, 3, 2, 1 equals to 8 factorial. In general, we define n factorial as shown on the screen. For example, let us find out how to evaluate the following expression 6 factorial. Solution: A 6 explanation equals to 6, 5, 4, 3, 2, 1, which is equal to 720. Using factorials, we see that the number of permutations of n objects is n exclamation. Let us look at another example. There are 6 explanation, permutations of the 6 letters of the word square. In how many of them is R the second letter? Solution: let R be the second letter. Then there are 5 ways to fill the first spot, 4 ways to fill the third, 3 ways to fill the fourth, and so on. There are 5 exclamation such permutations. Counting permutations. We next consider the permutations of a set of objects taken from a larger set. Suppose we have n items. How many ordered arrangements of R items can we form from these n items? The number of permutations is denoted by P n R. The n refers to the number of different items and the R refers to the number of them appearing in each arrangement. This is equivalent to finding how many different ordered arrangements of people we can get on our chairs if we have n people to choose from. We proceed as follows. The first chair can be filled by any of the n people, the second by any of the remaining n minus 1 people, and so on. The rth chair can be filled by n minus r plus 1 people. Hence, we easily see that permutation of p and r is given as shown on the screen. Example. How many ways can gold, silver and bronze medals be awarded for a race run by 8 people? Solution. Using the permutation formula, we find p, that is 8 and 3, in 336 ways. Did you know? A first case in which seemingly unrelated mathematical questions were studied with the help of permutations, which occurred around 1770 when Joseph Louis Lagrange, in the study of polynomial equations, observed that properties of the permutations of the roots of an equation are related to the possibilities to solve it. Now, moving on to the next topic, we will study combinations. As mentioned above, in a permutation, the order of the set of objects or people is taken into account. However, there are many problems in which we want to know the number of ways in which our objects can be selected from n distinct objects in arbitrary order. For example, when selecting a two-person committee from a club of 10 members, the order in the committee is irrelevant. That is, choosing Mr. A and Miss B in a committee is the same as choosing Miss B and Mr. A. A combination is a group of items in which the order does not make a difference. Counting combinations. Let's see n r denote the number of ways in which our objects can be selected from a set of n distinct objects. Since the number of groups of r elements out of n elements is c and r, and each group can be arranged in r exclamation ways, then p n r equals to r exclamation c n r. Let us now look at an example. How many ways are there to select a committee to develop a discrete mathematics course at a school if the committee is to consist of 3 faculty members from the mathematics department and 4 from the computer science department? If there are 9 faculty members of the math department and 11 of the CS department. For solution, carefully look at the screen. Finding probabilities using combinations and permutations. Combinations can be used in finding probabilities as illustrated in the next example. Example, given a class of 12 girls and 10 boys, in how many ways can a committee of 5 consisting of 3 girls and 2 boys be chosen? What is the probability that a committee of 5 chosen at random form from the class consists of 3 girls and 2 boys? How many of the possible committees of 5 have no boys, that is, they consist only of girls? What is the probability that a committee of 5 chosen at random from the class consists only of girls? The solution, we first note that the order of the children in the committee does not matter. From 12 girls, we can choose C, 3 different groups of 3 girls. From the 10 boys, we can choose C, 2 different groups. Thus, by the fundamental principle of counting, the total number of committees is as shown. The total number of committees of F of 5 is C, 5, which is equals to 26,334. The number of ways to choose 5 girls from the 12 girls in the class is as shown. The probability that a committee of 5 consists of girls is as shown on the screen. Let's know the meaning of binomial theorem. The binomial theorem was known to Indians and Greek mathematicians in the 3rd century BC for some cases. The credit for the result for natural exponents goes to the Arab poet and mathematician Omar Khayyam, AD 1048 to 1122. Further generalization to rational exponents was done by the British mathematician Newton, which was from AD 1642 to 1727. There was a reason for looking for further generalization apart from mathematical interest. The reason was that its many applications. Apart from the ones we mentioned at the beginning, the binomial theorem has several applications in probability theory, calculus, and in approximating numbers like 1.02, 7, 31 by 5, etc. Before discussing binomial theory, we shall introduce the concept of principle of mathematical induction, which we shall be using in proving the binomial theory for a positive integral index. This principle is also useful in making generalizations from different particular statements or results. What is a statement? In your daily interactions, you must have made several assertions in the form of sentences. Of these assertions, the ones that are either true or false are called statements or propositions. For instance, I am 20 years old. and if x equals to 3, then x square equals to 9 are statements. But when will you leave and how wonderful are not statements? Notice that a statement has to be a definite assertion which can be true or false but not both. For example, x minus 5 equals to 7 is not a statement because we don't know what x is. If x equals to 12, it is true, but if x equals to 5, it is not true. Therefore, x minus 5 equals to 7 is not accepted by mathematicians as a statement. Let's look at a few examples. Which of the following sentences is a statement? India has never had a woman president. 5 is an even number. Xn is greater than 1. A plus b square equals to a square plus 2ab plus b square. Solution. 1 and 2 are statements, 1 being true and 2 being false. 3 is not a statement since we cannot determine whether it is true or false unless we know the range of values that x and y can take. Now look at 4. At first glance, you may say that it is not a statement for the very same reasons that 3 is not. But look at 4 carefully. It is true for any value of a and b. It is an identity. Therefore, in this case, even though we have not specified the range of values for a and b, 4 is still a statement. Some statements like the one given are about natural numbers in general. Let us look at the statements given. This involves a general natural number, n. Let us call this statement Pn. P stands for proposition. Let us look at some examples to help you get used to this notation. If Pn is the statement as shown, then write P1, Pk and Pk plus 1. For solution, carefully look at the screen. The binomial theorem for a natural exponent. You must have multiplied a binomial by itself or by another binomial. Let us use this knowledge to do some expansions. Consider the binomial x plus y. Now look at the screen carefully. In each of the equations, the right-hand side is called the binomial expansion of the left-hand side. Note that in each of the above expansions, we have written the power of a binomial in the expanded form in such a way that the terms are in descending powers of the first term of the binomial, which is x in the above examples. If you look closely at these expansions, you would also observe the following. The number of the terms in the expansion is one more than the exponent of the binomial. For example, in the expansion of x plus y into 4, the number of terms is 5. The exponent of x in the first term is the same as the exponent of the binomial, and the exponent decreases by 1 in each successive term of the expansion. The exponent of y in the first term is 0 as y0 equals to 1. The exponent of y in the second term is 1 and it increases by 1 in each successive term till it becomes the exponent of the binomial in the last term of the expansion, 4. The sum of the exponents of x and y in each term is equal to the exponent of the binomial. For example, in the expansion of x plus y into 5, the sum of the exponents of x and y in each term is 5. If we use the combinatorial coefficient, we can write the expansion as it is shown on the screen. Binomial theorem for rational exponents. So far, you have applied the binomial theorem only when the binomial has been raised to a power which is a natural number. What happens if the exponent is a negative integer or if it is a fraction? We will state the results that allows us to still have a binomial expansion, but we will have infinite terms in this case. The result is a generalized version of the earlier binomial theorem which you have studied. Theorem. The binomial theorem for a rational exponent. If r is a rational number and x is a real number such that x is less than 1, then look at the screen for better understanding. Use of binomial theorem in approximations. As you have seen, the binomial expansions sometimes have infinitely many terms. In such cases, for further calculations, an approximate value involving only the first few terms may be enough for us. Let us illustrate some situations in which we find the approximate values. Find the cube root of 1.03 up to 3 decimal places. Carefully look at the screen to understand the solution. Now in the end, let us summarize what we have learned in this lecture. Alternatively, if we have n objects of which r are the same, then the number of distinct permutations is given by n factorial or by r factorial. If we know the total number of permutations for n objects, we obtain the number of combinations by dividing out the unwanted permutations generated by the order within each selection and the order within each set not selected. The number of permutations is denoted by P n r. The number of terms in the expansion is one more than the exponent of the binomial. For example, in the expansion of x plus y4, the number of the term is 5. The exponent of x in the first term is the same as the exponent of the binomial, and the exponent decreases by 1 in each successive term of the expansion.